Hi everyone. First of all, let me thank the organizers for having me today, and thank you all for tuning in for this talk. Today I'll be telling you a little bit about aggregation with differential privacy in the shuffle model. And if you haven't heard about differential privacy before or the shuffle model before, no worries at all. We will be giving the definition to all of those, so there is no particular preliminary required on privacy. The only thing that is perhaps required is some knowledge on probability, but just some basic knowledge. All right, so without further ado, let me get started. Today we'll be discussing distributed analytics scenarios, and this can be abstracted as follows. There are n users, and there is the analyzer. Each user I has some input xi, and based on the input and perhaps the randomness of the user has to produce some message yi. These messages are sent to the analyzer, who use them to compute an estimate of some function f on the x1 to xn. So this abstraction is a pretty generic abstraction, and it captures many problems in practical settings. And perhaps one of the most basic distributed analytic tasks is the task of counting. In this case, you have some criterion, and you want to count the number of users that satisfy such a criterion. And this can be modeled as follows. You can model each xi as either 0 or 1 based on whether the user satisfies the criteria. And the analyzer now want to estimate the sum of xi. Now, you don't want to just do this counting task, but you want to do it privately. Now, of course, there are many ways to define what it means for an algorithm to respect the user's privacy. And indeed, there are many definitions out there. Today, we'll be discussing the differential privacy notation. And in differential privacy, the intuition here is that we want the analyzer to output just the aggregate information without revealing too much about a single user. And the way we will model this in differential privacy is that if we change an output to a single user, then the output of the algorithm shouldn't change too much. And this can be captured in the following definition. And in this definition, there are two parameters, epsilon and delta. The smaller they are, the more private your algorithm would be. We say that an algorithm A is epsilon delta differentially private, or epsilon delta dp for short, if for all set S of outcomes, and for any two neighboring dataset x and x prime that result from changing a single user's input from the other, the probability that your algorithm, when run on x, has an output that belongs to S is at most e to the epsilon times the same probability but run on x prime plus delta. Now, this definition is a little bit mouthful, but if you haven't seen it before, perhaps the easiest way to visualize this is to think about the case where delta is equal to 0. And this case is often referred to as the PLDP, pure differential privacy case. In this case, the condition can be simplified as follows. For every outcome O, you just want the probability that your algorithm output this outcome on input X to be at most e to the epsilon times the same probability but on input X prime. In other words, changing a single user shouldn't change the probability of outputting a single outcome by at most an e to the epsilon factor multiplicatively. And as I said earlier, this delta equals to 0 is the so-called PLDP case, whereas the case where delta is greater than 0 is sometimes referred to as the approximate DP case. And for now, if you haven't seen DP before, you can think of the delta as the failure probability where your privacy leakage is greater than this e to the epsilon multiplicative factor. And since this is the failure probability, you want this to happen with very small probability. So the typical setting of delta is typically negligible in n, so it's 1 over something like n to the very large power, or 1 over super polynomial in n. Whereas the typical setting of epsilon is a constant, something like 1 or 0.1 and so on. So these are good to keep in mind. All right, so far I have tell you about the definition of differential privacy. But it turns out that this definition hasn't specified the entire model just yet. Why is that? Because I haven't told you what do I consider to be an algorithm. And indeed, if you consider a different scope of this protocol to be an algorithm, you will end up with a different model of differential privacy. Perhaps the most popular model, and indeed the original model, is the so-called central model, or sometimes referred to as the trusted curator model. In this model, you view the entire process from the user sending the messages to the analyzer producing the output as a single algorithm. And in this case, you only require the output of this entire process, which in our case is the estimate of the sum of xi, to be differentially private. It turns out that this central differential privacy is a pretty powerful model, and in the case of our problem of counting, we can get an algorithm with error that grows only as 1 over epsilon, which we will see in the next slide. And note here that this 1 over epsilon is quite small. As I said earlier, epsilon is only a constant, so this error is maybe in the order of 1 or 10 and so on. So if you have n that is even in the hundreds, you are in a great shape typically. Okay, so what is this algorithm? This algorithm is the so-called discrete Laplace mechanism, and it works as follows. So each user just sends their input to the analyzer, and the analyzer computes the true sum of xi, but it doesn't output that directly. It outputs that true sum plus some noise drawn from a distribution called the discrete Laplace distribution with parameter 1 over epsilon. And this discrete Laplace distribution is a probability distribution where the probability mass peak at the middle and the probability mass go down as you go further away from the center. It goes down geometrically, and in each step it goes down by a factor of e to the epsilon. So why is this algorithm differentially private? So let's consider two data sets, D and D prime. And as said earlier, if the data sets are neighboring, it means that only a single user's input change. So suppose that a user in D changed from 1 to 0 in D prime. Then you can see that after you add the Laplace noise, the probability mass will look like the one shown on the slide here. And if you look at any outcome, the ratio between the two probability masses is at most e to the epsilon. And this is why the algorithm is differentially private. And it's also not hard to show that the expected error of this mechanism is only 1 over epsilon. So this is indeed the epsilon dp algorithm with error 1 over epsilon in the central model. So far this is great, except that the central model also has its own downside. And what is that? As you can see in this protocol, each user I sends its own input to the analyzer. And here, if the analyzer is trusted, or if the xi is not particularly sensitive, then that might be fine. But in the case where you may not trust the analyzer, maybe the analyzer is some company or some government agency that you don't want to reveal your input to, then this might not be preferred. And you might also want to somehow protect your input xi from the analyzer as well. And this takes us to the next model called the local model. In this model, you will just the algorithm of each user to produce the message to be to be the algorithm, and that's the scope you would like to protect. And you are requiring that each yi be differentially private. And note that this is great in terms of trust, because everything that the user is sending to the analyzer is already differentially private. So whatever the analyzer does, it cannot learn too much about this user. However, this also comes at a price, because in the local DP model, the base algorithm for the summation problem, the counting problem that we are looking at, has an error of square root of n. And what is this algorithm? So this is a classic algorithm called randomized response, and it works as follows. So each user, instead of just sending its own input directly, it flips a coin and it sends its own input xi with a certain probability e to the epsilon over e to the epsilon plus 1. And with the remaining probability 1 over e to the epsilon plus 1, it sends 1 minus its own input. So it flips its inputs. And the point here is that the ratio between these two probabilities is only e to the epsilon. And this is why your algorithm is epsilon differentially private in the local model. Now, what does the analyzer do? The analyzer cannot just take the sum directly now, because if you look at the expectation is not right. So you have to debias. So you have to subtract the sum of yi by some number. In this case, is n over e to the epsilon plus 1. And then dividing it by e to the epsilon minus 1. And this will give you the unbiased estimator. And it's not hard to calculate the expected error. And the expected error here is square root n over epsilon. Now, as I have discussed so far, the local model is great. You don't have to trust the analyzer or anyone at all. Everything leaving your device is already private. But it has this large error. Whereas in the central model, as we saw earlier, has very small error. But you have to have a lot of trust in the central authority, in the central analyzer. And this leads a lot of researchers to consider several intermediate models that can get the best of both worlds. One such model is the so-called shuffle model, and the setting is similar to before, except that the messages of the user are now not directly sent to the analyzer. Instead, it is sent through the so-called shuffler, who randomly permutes these messages. These permuted messages are then sent to the analyzer. Our new requirement here is just that these shuffle messages have to be differentially private. Or in other words, we require the multiset of messages to be differentially private. And note here that as long as we are able to perform this shuffling, we would be able to guarantee our privacy even against the analyzer. And therefore, we have relaxed the trust requirement from the central model. As you might have already noticed, shuffling the messages is also equivalent to anonymizing the sender of the messages, and this is why the model is also called the anonymous model in the crypto community. It's also called the encode, shuffle, and analyze architecture as well. And one of the fundamental and very powerful theorem regarding the shuffle model is the so-called amplification by shuffling theorem. This theorem, roughly speaking, says that if you take a local DP algorithm and run it instead in the shuffle model, then you get for free your amplification in differential privacy. In other words, if you take some epsilon L local DP algorithm and run it in the shuffle model, you get epsilon delta DP in the shuffle model, where epsilon is much smaller than the original epsilon L. If you select delta to be some reasonable value. This theorem was originally proved by Erglingson, and multiple versions of the theorem are now known with a better quantitative relation between epsilon and the original epsilon L. Okay, now that we have described our shuffle model, let us turn our attention back to the counting problem. As we already discussed in the central DP, we can get an error of 1 over epsilon, and each user just have to send their own input, so the number of bits sent is also just 1. In local DP, as we saw before as well, randomized response give us an error of square root n over epsilon, and each user either send its own input or the flipped bit, so still each user still send just 1 bit. Now, as I said earlier, in shuffle DP, if you take just the local DP algorithm and run it in shuffle DP, you already get a better dependency on the epsilon. And in this case, if you just take the randomized response that we already saw for local DP and run it in the shuffle model, you actually get a dramatic decrease in the error. So your error goes down from square root n to instead square root of log 1 over delta. And if you don't set delta to be too small, this square root log 1 over delta can be much smaller than square root n. But still, this square root log 1 over delta over epsilon is not quite the same as in the central model, where there is no dependency on the delta at all. So you might be wondering whether it's possible in the shuffle model to get the 1 over epsilon error as in the central model. Unfortunately, we were able to show that this is not possible, and indeed you have to pay an error that is at least square root log of 1 over delta in the shuffle model. So this is the end of the story for counting problem, is it? Well, not really, and the reason is that this lower bound only holds in the case that each user can send just a single message. And to overcome this lower bound, we will take a look at yet another relaxation of the shuffle model in the multi-message setting, where each user are now allowed to send multiple messages, and all these messages are shuffled together and then sent to the analyzer, who then produce the estimate similar to before. And similar to the single message case, we only require that these shuffled messages be differentially private. Turns out that if we allow multiple messages, we can in fact match the error in the central model, which is the 1 over epsilon here. And the earlier works that get this result have the number of bits that each user send blow up from just 1 bit to something like log of n over delta. And later, this communication was also improved, where the expected number of bits sent per user is nearly 1, is 1 plus some term that is pretty small. The exact dependency is something like polylogarithmic in 1 over delta over n. So if you don't set if you don't set delta to be too small, this second term is little or 1. It vanishes as n goes to infinity. Now, I would also like to mention that even though all the algorithm we discussed so far has delta greater than 0, there are also work that show that you can also get a good counting algorithm with delta equals to 0 as well. But these algorithms are a little bit less efficient. Specifically, to get an error of 1 over epsilon, the current base algorithm has to send roughly square root n bits per user, which obviously is much larger than some polylog or 1 plus little or 1. And they are also more complicated, so I will not go into too much detail about these two works in this talk. Instead, I will focus on the two algorithms that I mentioned earlier that has the same error as in the central model, but with the delta greater than 0. Okay, so far we have discussed the counting problem, where each user has an input xi that is either 0 or 1. It turns out that many of the techniques from the counting problem also apply to a slightly more general problem, which we will call here real summation. Here, instead of having a binary input, each user have a real value number between 0 to 1, and the goal again is to estimate the sum of xi. Okay, it turns out that the result in the central DP and local DP more or less holds as before, so you get 1 over epsilon and square root n over epsilon error. Each user only have to send 1 message. But now the number of bits that you need to send per user grows with something like logarithmic in n. In terms of shuffle DP, you can again use the local DP algorithm, and that has a single message. But it turns out that in this case, instead of getting to just a polylog 1 over delta error as we saw earlier, is not that simple here. And in fact, the error remains polynomial in n. Is the exact error is n to the 1/6. And in fact, Bale et al. Showed us this n to the 1/6 is tight. So if you allow a single message, you cannot get an error that is smaller than n to the 1/6. But once again, if you allow multiple messages, you can bypass this. So Shu et al. Shows that they can get polylog 1 over delta over epsilon, but they require a lot of messages. And the two work that I told you earlier about counting, it turns out that techniques also apply to real summation, and they get a fairly similar result to before for real summation as well, except that now the number of bits per messages is log n. And finally, the works with delta equals to 0, the PLDP work, also apply here with a slight bit more of a blow up. And as I said earlier, I will just focus on the two algorithms in the shuffle DP model that almost match the central DP guarantee, but with delta greater than 0. Okay, so those are the results that we'll be focusing on. Now, working with real summation can be a little bit awkward because the input is not discrete, but is a real number. Fortunately for us, Bale et al. Showed that it's pretty simple to reduce the discrete case, reduce the continuous case to the discrete case. And it works as follows. So the problem we will reduce to is the integer summation problem. But now each xi can belong to 0 and so on to some parameter big delta. So big delta will be greater than 1. So this will be more general than the counting problem that we discussed earlier. The reaction is very simple. So you replace xi by randomly rounding delta times xi. Bale et al. Shows that if you take this big delta to be roughly square root n, then the error from this discretization is negligible compared to the error from the noise that you are adding from differential privacy. And the main result that we will be seeing today, we'll be focusing on this discrete case of the integer summation for delta. There are two main techniques that will be used here. The first technique is what I will call here distributed noise addition. Remember that in the central model, we were using the discrete Laplace mechanism, which just means that we compute the sum, and we add to the sum some noise, and in this case, we add to it the noise drawn from the Laplace discrete Laplace mechanism. And note here that even though our input xi is now not 0, 1, but 0 to so on to big delta, the algorithm still works. You just have to scale up the parameter of the discrete Laplace by a factor of big delta. And you get the epsilon central DP algorithm with error order of delta over epsilon. So this algorithm belongs to a class of algorithm called additive noise mechanisms, which simply computes the true error and add to it some noise that is drawn from some distribution D. For simplicity here, I will just replace the noise drawn from D by just plus D here. And we have seen before the distribution D being discrete Laplace, but you can also choose other distribution like Gaussian or its discrete variant. And these different distribution will give you different utility guarantee and different privacy guarantees. And our main challenge here in the distributed setting in the shuffle model is that there is no central authority, there is no central analyzer to add this noise. So what this means is that the noise has to be added separately from all the users. In other words, we want to somehow divide this noise among all the end users. And the way we will do this is to use a property of distribution called infinitely divisible. A distribution is said to be infinitely divisible if for every integer n, you can find another distribution. Here I'm denoting it by the subscript divided by n, such that if you take n IID samples from D divided by n and sum them up, it's distributed as the original distribution that you want, the distribution D. And this is very nice because this means that each user can sample their noise from this D subscript divided by n. And when you sum all this noise up, the noise will be distributed exactly the same as the entire distribution D. So you get back your noise that you would have added in the central model. So before I continue, let me note that there are many distributions that are infinitely divisible. Perhaps the one that you might have heard of is the Poisson distribution. So if you take a Poisson two independent Poisson random variable and sum them up, then their parameters, their mean adds up. And in this case, what this means is that if you start with a Poisson with parameter lambda, then you can infinitely divide, and this D divided by n will just be dividing the parameter by a factor of n. There are also other examples such as the negative binomial distribution. And more importantly, the discrete Laplace distribution itself is also infinitely divisible. And this can be seen by writing discrete Laplace as a difference of two independent negative binomial distribution. So if you haven't seen the definition of Poisson or negative binomial before, then there is no need to worry about it too much, since we are not going to use the exact definition here. But one thing I will note here, which will come back at the later part of the talk, is that the Poisson and the negative binomial distribution are distribution on non-negative integers, whereas the discrete Laplace distribution, as we had seen earlier, is supported on all integers, meaning that sometimes is a negative value, sometimes a positive value, and sometimes it's 0. Okay, so that's all we will say for now for the noise addition part. Let us now move on to the second technique that will be used in coming up with the protocols for counting and real summation in the shuffle model. And this is a technique that is sometimes called split and mix technique. We will see 3 initialization of this technique. All of them share the same core idea, but they're slightly different, and they will give different guarantee for the different protocols. And the general idea for split and mix is very simple. Suppose that you are a user. You want to send a single integer. Now, you can, instead of sending this as a single message, you split this integer into multiple integers whose sum is equal to the original integer you want to send. Now, these multiple integers that you have split, you send them. In shuffling, all these many integers that got split from the original integer gets mixed together. And intuitively, this should make your algorithm more private. Alright, so let's see this technique in action, and we will start with the most basic protocol. So the root of this protocol actually comes from the work of shai et al. in crypto literature. So let me start by defining a slightly different notion, which I will call security here instead of privacy to avoid confusion. And in security, the setting is the same as before, except that now each xi is from some field CQ. And the security says that if you have two sets of xi's whose sum are equal, then if you look at the distribution of the shuffled messages, that distribution shouldn't be different in the total variation distance. And note here that now there is no epsilon. You can think of epsilon as 1. And another important point is that you have to be secure against any two input whose sum are the same. And these two input, they can change many users as long as the sums are the same. So these are the difference between the two settings. So the algorithm by shai et al. Is very simple, and is to generate random shares of x. What do I mean by this? What I mean by this is, first you take the first m-1 messages, y1 to ym-1, to just be a random element of your field. And then you set the last message to be x minus the sum of your first m minus 1 messages. So this is very simple, right? For the analyzer just add all the messages up. Since you are just splitting your integer and mixing them up, the sum is always correct. Now, in terms of utility, shai et al. Shows that the protocol is sigma secure, where sigma is the security parameter. When m is something like sigma plus log q, this number of messages m was improved recently by a factor of log n, which also improved the communication of the protocol. Okay, so this is a security setting. So how do you use it in the differential privacy setting? Here's how. So first you pick Q to be a sufficiently large field. So in our case, Q can be something like n squared here. This would work. And then instead of letting your last message be x minus the sum, you let your last message be x plus the distributed noise minus the sum. And the analyzer again just add all the messages up. And what is the point here? The point here is that the sum after noise addition is the same as the sum plus a single discrete Laplace noise as in the central model. And in terms of privacy, it's possible to show that security implies privacy. And the intuition is that security is, once again, sort of a probability that you are leaking the input. Again, this is not very accurate, but it's a rough idea. And if you have a certain probability of leaking the input, but the rest you are completely secure, this failure probability also translates to the failure probability delta in your differential privacy as well. And that's why you get the epsilon delta dp, where delta is roughly the same as 2 minus the security parameter. And here, in terms of setting a parameter, now you have to set delta to be log 1 over delta. The security parameter sigma to be log 1 over delta. But this is kind of not so great, because it means that the number of messages that you need, the m, is log of 1 over delta over log n. And this can be pretty large if you set delta to be somewhat small. And in fact, all this analysis require the number of messages that you split into to be at least 3. So every user has to send at least 3 messages. And also note here that the field size q has to be polynomial in n. So each message also has length log n. These are not so great, given that in the non-private setting, each user has to send only a single message with 1 bit in the case of counting. And you want to roughly match that as well in the differential privacy setting. And we will now see how to do that. And once again, we will use split and mix, but with a different twist to it. And just to make sure we are on the same page, here we will be focusing on for counting for the moment. We will go back to the more general case of integer summation later on in the talk. Okay, so what would you do as a first attempt if you want to design a counting algorithm that sends few bits and each message being small bits as well? So here is one possible attempt. So suppose you have your infinitely divisible noise d that you wanna add. Then each user can do the following. They will sample the distributed noise they wanna add from d divided by n here. And then they will send the messages that are all the same. Here I'm denoting these messages by 1. They are exactly the same messages, except they just vary the number of these messages. And the number of these messages that they will send will be the noise z plus x, the input. Okay? And what does the analyzer do? The analyzer again just return the sum of all messages. Or in this case, since all messages are 1, you just return the count. They are equivalent. Okay, so why is this good for us? Let's think about what exactly does the analyzer sees. The analyzer, since all the messages are the same, the analyzer only sees the number of ones that it gets, right? Because everything got completely shuffled. And what is the number of ones it gets? It's just the sum of the input plus the sum of this distributed noise. But as we said earlier, we are taking the noise from the divided from the central noise. So when you add up this NIID noise, you just get back a single noise term that is distributed as D. Okay, so this is fantastic because this is exactly the same as the additive noise mechanism in the central model. You get the same utility and you also get exactly the same privacy. Okay, so this is great, right? But as you can see, this is our first attempt, so something is wrong here. And what is wrong here is that you cannot send negative number of messages, right? That's not allowed. That's undefined. And that's exactly the problem. If you try to initialize this protocol with, say, a discrete Laplace distribution, then there is a certain probability that your noise will be negative. And then you would want to send negative number of messages, which cannot be done. So this protocol is actually only valid if your noise distribution D is non-negative. And the bad news here is that if you restrict to only a family of non-negative noise, then you will still have to suffer an error of log 1 over delta. This can be proved. It's not very hard, but I will not go into detail here. So this idea is close to what we want, but not really quite enough yet. So we want to be able to support negative noise as well. So what should we do? Well, you want to support negative noise. Let's try to also send minus ones, right? Not just plus one. Let's do minus one as well. And here the protocol will be similar to before, except that I'm also sampling this Z minus from the same distribution. And I'm going to send Z plus X plus 1 messages, and then C minus minus 1 messages. Okay, the analyzer again the same as before, just the sum of all messages. Now, what does the analyzer see? There are now two types of messages, plus 1 and minus 1. So they will see the number of plus 1s and the number of minus 1, the total across all the users, since this is after shuffling. And the total number of plus 1 will be the sum of xi plus a random variable drawn from D. And the number of minus 1 will just be a random variable drawn from D as well. In terms of the utility, since the estimate is just the sum of all messages, it will be the sum of xi plus a copy of random variable from D minus another IID copy. So if you take D to be an appropriate parameter, this D minus D term will be exactly the discrete Laplace. So you get the same utility as the discrete Laplace mechanism. Okay, so that's great. So far, so great. How about privacy? Well, unfortunately, it doesn't quite work. And without going into too much detail, the reason is roughly that if you think about this, right, you are leaking the number of plus 1. But the number of plus 1 is actually sum of xi plus this D. But now your D is not exactly the discrete Laplace, right? You are selecting D so that D minus D is a discrete Laplace. So your D is kind of half of the noise if you want to think about it that way. And this half of the noise is not enough to get the same privacy as the full noise that you get in the central model. So the privacy still doesn't work here, so it's still not enough, our second attempt here. Okay, so let's try to fix this. And how do we fix this? We'll use a split and mix technique. Okay? Remember that we want the utility to be the same as before, but we somehow want a better privacy. So what do? We will sample another term y from another different distribution d prime divided by n. And we will do everything the same as before, except that we are now sending an additional, in addition to the messages we sent before, we will send y additional plus 1 messages and y additional minus 1 messages. And note here that this is a kind of a split and mix, but using plus 1 and minus 1, because now the extra messages that we are sending, plus 1, like y plus 1 and y minus 1, sum up to 0. So there is no effect on the utility. How about the privacy? why does this help in terms of privacy? Again, similar to before, the analyzer will get to see the number of +1 and the number of -1. And you can write the number, I'm going to write the number of +1 as u1 and the number of -1 as u-1. So seeing u1 and u-1 is equivalent to seeing u1 minus u-1 and u-1. And the first term is exactly the discrete Laplace mechanism. How about the second term? Now, this second term is z minus plus y. It has some correlation with the first term, but the y only appear in the second term, not in the first term. And it turns out that if you select the distribution d prime, the one that y is sampled from, to be large enough, then this second term and the first term has sufficiently low correlation. You kind of destroy the correlation between the two, so that basically the second term doesn't leak any privacy. And this is why essentially the privacy leak all come from the second term, which is exactly the same as the discrete Laplace mechanism. And that's why you get the differential privacy that you want. Now let me quickly discuss the communication complexity for a moment. So each message that you send has 1 bit. How about the number of messages that you send? What is the expected number of messages that you send? Is the expectation of x plus z plus c minus plus 2y, and the 2 come from the fact that you send +1 y times and -1 y times. Okay, and x is at most 1. Both c and z minus are drawn from the d divided by n distribution, and the y is drawn from d prime divided by n distribution. So the last 3 terms reduce to just 2 times the expectation of this d divided by n and d prime divided by n distribution. But the point here is that this is the noise that is already divided across n user. So their expectation is just the expectation of the combined noise d and d prime, the entire thing divided by n. And this expectation of d and expectation of d prime is already pretty small. So I didn't go into too much detail about the setting of parameter, but you can set it so that the maximum of these 2 terms is only polylogarithmic in 1 over delta. And that's why in the second term you only get polylogarithmic in 1 over delta divided by n, which when delta is not too small will be negligible. Just to summarize, what we have is an epsilon delta dp algorithm in the shuffle model that has the same error as 0.99 epsilon dp discrete Laplace mechanism in the central model. And in expectation, each user sends just 1 plus order of log square 1 over delta over n messages, and each message is 1 bit. So in expectation, each user sends just 1 plus little or 1 bit, as long as you set delta not too small, like not smaller than 2 to the minus square root n. So it's achieve a nearly central DP performance. But in the shuffle model, which as we discussed earlier, require weaker trust. Okay, so this is great. So far we discussed the split and mix in the counting setting where each xi is 0 and 1. In the last part of this talk, let's try to extend this 0 and 1 setting to the integer setting where each xi can be from 0 to big delta. Okay, so I'm just copying here the protocol from before. It is exactly the same as before. Now, suppose that we are running the same protocol in this setting. What is the problem? Okay, utility, turns out utility is fine. In fact, privacy is also fine. The only issue is this. You are sending x plus 1 messages, regardless of the noise term. You are sending at least x plus 1 messages. But now our x can be as large as this big delta, right? X is not just 0, 1 anymore. So if x is, say, big delta, you are always sending at least big delta messages. And this big delta can be large. Just to recall, the reduction from real summation to integer summation has big delta being square root n. So this means that each user would send square root n messages, and that's clearly too large. And we want to reduce this. We want to reduce these big delta messages to just close to one message. And note here that we cannot do that if we are sending just +1 and -1 messages, right? There are not enough information for us to encode our input in one message. So we are forced to send messages that are now at least minus delta, minus big delta to plus big delta. And that's exactly what we'll try to do. Let's try the first attempt. Instead of sending x +1, just send x as a message itself, and the remaining of the protocol is the same as before. Okay, so if you work out the calculation, you see that the number of messages is fine, the utility is also fine. But now you have a privacy issue because all the noise are added to the +1 and -1 messages, but there is no noise at all added to the +2 and so on to plus delta messages. And these are reviewed directly, and since there are no noise, this is not going to be differentially private. Okay, so we want to fix this. And we'll fix this by just adding noise to those numbers, right? And we'll do this by, again, split and mix, which just means that we are adding more messages whose sums are 0. And the modification, the exact modification is not too important, but we will select a certain family of sets from that are subsets of minus delta to delta whose sum is 0. And then we will sample a random variable which tells us how many copy of these subsets we are going to send. For example, if our set S is +1 +1 -2, and we sample this random variable CS to be 2, then we will send +1 in addition 4 more times and -2 2 more times. And the intuition is exactly the same as before. If you add zero-sum noise, it's draw out any information except the sum. And we already know that the sum itself is dp because it's the same as the discrete Laplace mechanism. And in terms of the privacy analysis, is the generalization of the privacy analysis that we saw earlier for the counting case. Basically, the analyzer view here will be the number of each type of messages, meaning the number of plus delta messages, the number of plus delta -1 messages, and so on and so forth, to the number of minus delta messages. And each type of message has its own noise, which is represented by this CS, where set S are like the set of numbers whose sum are 0. And it turns out that if we choose this carefully enough, we can again do this subtraction and addition trick as before, so that most of the term cancel out and we end up with some easy term that we can analyze similar to before. Alright, so that's all the technical material that I have for today. I hope you all learn a little bit more about differential privacy in general and also about aggregation with differential privacy in the shuffle model in particular. Thank you all very much for your attention.